Okay, welcome back. This is Mr. Wakefield again, and we're looking at section 2.6 now. You can see here at the top of the page that it has these things called basic graphs. We haven't seen this graphs before. We have not seen them, but um, we're going to see them little by little here in each of the next couple of sections so that by the end of section 2.7, you'll be familiar with all of them. For now, though, we're just going to look at them as they come up on each problem, okay? We won't look at all of them right now, but we will see them all eventually. Now, in this next thing down here, it says... it talks about the word continuous. A continuous function is something where when you look at its graph, you guys, you can actually draw the entire graph from one side to the other without picking your pencil up off of the paper. You can see that I can do that here on this graph here. In fact, you can do it on all 5 of these. All 5 of these graphs can be drawn as you move from left to right without picking your pencil up off the paper. Now you might be thinking, hey, aren't all graphs like that? Actually not. Okay, most of them are, but if you look back here on the back side, sometimes graphs come in different pieces that are disconnected from each other. In other words, they're discontinuous, okay? All 3 of these are examples of that, okay? This one's almost connected, but it's kind of like there's a pothole in the road right there where somebody took something out of the road and they placed it over here right above it. Okay, so these are all discontinuous graphs, but yes, it is true that most graphs are continuous. Okay, we'll get to these problems here in a little bit. But let's go back to the front and let's look at that example problem there. Not a numbered problem, but just an example problem here. They want us to graph this thing right here. Okay, and it says here, it describes this as a piecewise function, meaning that it's going to come in different pieces right here. It doesn't mean it's always discontinuous, as we're going to find out. But piecewise means that f of x means different things based on what your x's are equal to. Okay, so let's talk about that here. When you graph something like this, what it means is that we graph each one of these parts, but only a portion of each one of the graphs actually goes on there, okay? But let's not worry about that yet. Let's first of all focus on both of these different graphs and what they're looking like. So since f of x is equal to these two things, remember you guys that f of x is the same thing as y, isn't it? Okay, so it's as if we're graphing y equal to x squared, and it's as if we're graphing y equal to x plus 1. Now, we know how to graph both of those things because y equal to x squared is up here at the top of the page, okay? And then y equal to x plus 1, that's actually mx plus b right there. So I'll get to that in a minute. But first of all, y equal to x squared, again, that looks like this graph up here. But it says x greater than or equal to 0 next to it. What that means is you only graph the portion of it where x is either equal to 0 or greater than. Remember, greater than means to the right. Okay, greater than means to the right. And so you only graph the portion of x squared which is to the right of 0. In other words, this part right here, you guys, to the right of where the x equal to 0 is. Okay, because greater than means to the right. And so let's do that right now. Okay. And I'm going to put all the details on there that they have from the graph on the top of the page there, where it says up there that 0, 0 is one of the points, 1, 1 is one of the points, and 2, 4 is one of the points. So I'm going to, just to give sufficient detail there, I'm going to put that in there, and then there is the portion of that graph. Just that portion that is above, or that is to the right of 0. Okay, now what about this here? This here is mx plus b. Since that is 1x plus 1 right there, we know there's an invisible 1 there, which I wrote down just to make that clear. That means that the m is equal to 1 over 1, isn't it? Since the number in front of x is equal to 1, and 1 over 1 is the same thing as that. But we also know that the b is equal to 1, as we learned back in section 2.4 and in 2.5. Mx plus b, the b would then be equal to 1 right here after the plus. So how does that work? Well, normally the graph would look like what? And be careful with this, all right? Don't draw it really dark yet. I'm going to actually pull up my eraser and erase part of this off here in just a moment. But normally what you would do in that graph is you'd put the point right here, okay? And then, because you always start out with B when you use the M and the B for your graph, just like we learned before. And then 1 over 1 means that we rise 1 and we run 1, because that's a positive slope. Rise 1 and run 1, that would bring you right there. So normally the graph would look like this right here, okay? However, there's a problem with that, okay? The problem is that it says that this graph only applies to when x is less than 0. That means when x is to the left of 0. That means that the portion of that line that I just drew that is to the right of 0 needs to be removed. We only want the part that is to the left of 0 there. And I'm going to have to kind of erase part of my previous graph there. I'll put it back on, but I just wanted to make sure I got that previous part off of there. Okay. The previous part of the line, that is. And so we got this right here. Okay. And so then this part of the line stays. Okay. Now there's one more thing that we got to do, and that is, in order to be completely clear here, is what's going on right where the definition of the formula changes. As you can see here, the definition of the formula changes at 0. When that happens, what oftentimes occurs at that number 0 is that you're going to have some open circles and some closed circles. Okay. When you have one of the formulas being strictly less than 0, in other words, it doesn't have the alligator feet underneath the alligator mouth right there, that means that we're going to have an open circle, not colored in, at that point right there. So I'm going to put an open circle right there at 0, still in the same point it was at before, okay, but it's just an open circle now. Okay, let me zoom in there on that. I know that's kind of small there on the screen. See how we got the open circle right there? Okay, but then this is going to be a closed circle. The reason why is because that comes from the first graph, and in the first graph, the alligator has a foot underneath him, okay? The alligator mouth has a foot underneath him. In other words, he's got the equal to thing underneath the alligator mouth. So that is going to be a closed circle, meaning it's a colored in circle. And so let me just highlight that extra clear here. There we go. All right, so this one is an open circle because it comes from the second formula, and the second formula did not have the alligator feet. This one right here is an open circle because it came from the first formula, and the first formula did have the alligator feet. Okay, so that's how you do a piecewise graph. You do each piece one at a time, but you only keep the part that applies to the condition here to the right, where it says x is to the right of 0 and x is to the left of 0. Okay. There's one additional thing we're going to need to do on the next couple of problems, but we'll see that. But basically, that's the idea there. Let's take a look at those next two problems, as a matter of fact. And just to point out, by the way, you guys, I didn't mean to skip this one right here, number 1. I will come back to that at the end, okay? But as long as we're on the topic of graphing, I want to continue on right now with that discussion with problems 2 and 3, okay? So let's do that. So in number 2, we have what? We have f of x equal to 2 different things once again. The definition of the function formulas are going to change at 3. That's going to be important. We'll talk about that. We've got an alligator feet right here and then no alligator feet here. So that means that this is going to be there's going to be a closed circle there. But then there's going to be an open circle on this one. Again, we'll get to all this, okay? But I'm just kind of pointing this out right now, okay? And then we've got 2 different formulas here. We've got f of x, which is the same thing as y equal to 6 minus x, okay? And then we've got f of x, which is the same thing as y equal to 3, okay? Sorry, that fell off the screen there. There we go. Now remember, 6 minus x is the same thing as negative x plus 6. Negative x plus 6. Okay, just reversing the terms around. Okay, so that means that this is mx plus b again. We have negative 1 in front of the x there, and so the slope is negative 1 over 1. The b is 6, as you can see there, and I should probably reposition that there because that's going to get in the way of my graph here, as you find out in just a minute. But it is equal to 6 nonetheless, though. So we have b equal to 6 here. It actually won't get in the way if I put it here, so I'll put it here. Remember, though, when I graph this, which I'm about ready to do, we only want to graph the part that is less than or equal to 3. That means we want to go to the left of 3. Less than means to the left. Okay, so if the variable is less than, you always go to the left, just like we've seen before with inequality problems. Okay, so here's 3, right? This is where x is equal to 3, right? So any portion of the graph that is to the left of that, we want to keep that, and anything that is over here, we don't keep that. Okay, so let me go ahead and just graph it as normal. The y-intercept is 6. Let's count that out. 1, 2, 3, 4, 5, 6. So I'm going to just extend my graph here a little bit. There's 6 right there. Okay. And so I'm going to put my y-intercept right there. And then negative 1 over 1, since that's a negative slope, I am going to drop 1 and run 1. Drop 1 and run 1. That's going to take me right there. Okay, and now again, draw this lightly because we're going to eventually need to erase it off, so we don't want to draw it too dark yet. But we're going to get this right here. Okay, all right, like that. But what did it say? It says we only want to keep the part that is what? That is to the left of the 3. So let me erase off that part right there. Okay. When you erase off one side of a line, remember, you're not going to have an arrow on that side because arrow means it goes on forever. But this graph is supposed to stop at 3. It's just supposed to be on the left of 3, so it has to stop there. Now, do I put a closed circle there? Yes, I do, because with 6 minus x, which is what I'm graphing right now, it is supposed to be a closed circle. So I put a closed circle right there where it ends, okay, at 3. And then let's now do the other graph, y equal to 3. As we learned, you guys, back in a previous section, section 2.4, just give me a moment here to pull that out, and I'll pull that out for you. Here it is. We know that when you have y equal to something, okay, and no x, y by itself equal to something, that line is always going to be horizontal. In fact, this one is exactly the same thing as what we're looking at right now. It's y equal to 3. But if it was y equal to 4 or y equal to 6, if there's no x, then that's what happens, okay? It is horizontal. So that's exactly what happens here. This graph right here is horizontal, okay? You take what y is equal to, you find it on the y-axis, and then you just draw a horizontal line through that. Okay, but remember, when I draw it, I only want the portion. I only want to keep the portion that is greater than 3, which means I only want to keep the portion that is to the right of the 3. And so when I draw the horizontal line, I don't really have to draw the whole thing. You can if you want to, as long as you're ready to erase off the part that you don't need. But we only need to keep this part right here. Okay, like that, to the right of 3. Okay, now normally at this point we would do an open circle. Okay, remember we do our open and closed circles where the graphs change their formula from one to the other, from one formula to the other here, 6 minus x to 3. So like I said, on this one it's going to be an open circle, but here's the problem here, okay? Theoretically, you do put an open circle right here because this tells us to do that, but don't be alarmed if you put an open circle here and it still looks like a closed circle. Because notice that the open circle and the closed circle are both on exactly the same point here, and I'll confirm that here in just a second. I'll show you how to be sure that it really does land on the same point. Because sometimes our graphs can be a little bit off, you know. Okay, sometimes our lines aren't completely straight. But for now, I'll just tell you that it really will, even after we confirm it, it really will, both of these parts of these graphs will really land on the same spot right here. All right. And when you put an open circle on top of a closed circle, you can't see the open circle, can you? Because the closed circle is actually coloring in the open circle that's not supposed to be there. So if you've got a closed circle and an open circle in the same spot, okay, it should look like a closed circle, and there's nothing wrong with that. Okay, don't be alarmed by that. But normally, as we see down here in number 4, and as we saw in the last problem, normally you're going to have a closed circle and an open circle. Okay, but it's just because they both land on the same spot this time that it's different. Okay, now one other thing we need to do in order to make sure that each one of our graphs ends at the correct spot. It doesn't have to be the same spot like it was here, but it has to end in the correct spot, is that you need to do this. You need to take where it changes right there. The graph changes at x equal to 3. So here's what you do. You take x equal to 3, and you plug it into both of these two things right here. Changes at x equal to 3. Sorry, that fell off the screen. Let me zoom out for you. So it changes there, and so if we plug in 3 into both of these, and there's no place to plug it in here, but you at least try to. If there's no variable, then you just keep it as 3, but here it would be 6 minus 3. Notice that both of these answers, though, are equal to 3. Okay, 3 is equal to 3, and 6 minus 3 is equal to 3. That's what the y value is, because these things right here, when you plug them in, they are equal to f of x, which is the y value. So you take the number where it changes, you guys, you plug it into both of these, okay, and whatever numbers you end up with, that's the y value where that portion of the graph ends. Okay, so this diagonal line ends here because that's y equal to 3 right there. Let me write that down, y equal to 3. And then this portion of the graph, when it comes this way, it ends right here. And that also ends at 3, and that's why they land on the same spot. Okay, because the x's are both equal to 3, and the y's are both the same also. They're also equal to 3. But not, like I said, normally it won't be the same number. But you have to do this thing up here at the top in order to make sure that your graphs are landing on the correct spot when they actually stop, okay, when they change, and they both change at 3. Okay, the reason why I didn't do that last step on the previous problem, you guys, okay, you can see here that the graphs ended at 0. This one as it went up to up here to 0, and this one as it came down to 0. 0 is where they both end, x equal to 0. But I already was certain that the graphs actually ended at y equal to 1 for the open circle and y equal to 0 for the closed circle, because I knew exactly what the graphs look like at x equal to 0. I knew that the y-intercept was at x equal to 0, okay, because x equal to 0 is right on the y-axis. So I knew that that open circle was exactly on that spot, and I knew that this point was right exactly at 0, 0 because the graph at the top of the page told me that. Okay, you can see here that it says that 0, 0 is one of those points there. So that's the only reason why I skipped that last step there on that problem. But theoretically, you do need to do this thing right here where you plug in the number where the x's change, and that would be 3 here, to figure out what the y values are there so you know where your graphs end. Okay. All right. On this next problem here, you can see that it's even bigger this time. We've got 3 different ones this time. Okay. So we got to be careful with that. Once again, there's actually this time there's 2 different places that the graph changes at. It changes at -3. And it also changes at 2, okay? So you've got to the left of -3, and then you've got in between -3 and 2. When it's written like this, that's what that means. So we've got less than -3, which means to the left of -3. Let me write that down. So there's -3 right there. To the left of -3 is going to be the first part of the graph. Between -3 and 2 is going to be the second part of the graph here in the middle. And then x greater than 2 means to the right of 2, doesn't it? Okay, so that'll be that third part will be over here. Okay, so that means that it changes at x equal to -3 and x equal to 2. So we'll check out what's going on there, just like we did over here on this problem at the top here. But first things first here, y equal to -2x, y equal to 3x minus 1, and y equal to -4x. It's as if we're graphing three different things, just like in the previous two problems where we were graphing two different things. Now we're graphing three because there's three parts to this piecewise function. Okay. Please notice, you guys, that all three of these fit into the mx plus b form. Okay. I know the b is missing from a couple of those. But notice that, let me just make a little chart right here. The m and the b here for the first one is going to be -2 over 1. Okay, -2 over 1. Zoom in there for you. Okay, and then the b is 0 because the b is missing, right? I'm talking about the first one here. The second one here, it is 3 over 1. Let me fix my pencil there. Okay, 3 over 1. And -1, all right? And then the last one here is -4 over 1, and then the b is missing, so we call that 0. Okay? So we can now graph all of those, but again, you just need to graph the pieces that are needed. So the first one would normally be -2x. So normally you would graph what? Normally you would graph, again, don't graph this too dark yet because we're going to erase some of it. But we would normally start at b equal to 0, and then we would go down 2 and over 1. Okay, but there's a problem here. This graph is really not big enough for this. Just because the y, and you're going to find this out here, okay? It's kind of hard for you to see it yet, but since I've already done this problem, I'll tell you right now. What I'm going to do, you don't have to do this with the x's, but what I'm going to do with the y's is I'm going to go by 2s. I'm going to go 2, 4, 6, 8, 10. It's okay for you to do that as long as you tell me that. If you don't tell me that you're going to change the scale, then you have to stick with the 1, 2, 3, 4, 5 normal scaling, okay? But if you are going to do that scale, which you are allowed to do normally when you have graphs like this, you're allowed to do a different one for y as you are for x. So the x can stay as 1, 2, 3, 4 while this one changes. That is completely fine. It'll still be accurate. It'll look a little bit different than it would have if you had done the normal scale, but it'll still be accurate, just in a different kind of scaling, okay? So anyway, if I do it that way, then wouldn't this be -2 down here? Okay. And it has to be the same scaling from top to bottom here. Pardon me if I already mentioned that, but it is got to be the same. So this has got to be -2, this has got to be -4, and so on. So when I go down 2 and over 1, it's actually going to look like I'm going down 1 and over 1 because this actually counts for 2 right here. Okay, so when I go down 2 and over 1, it actually ends up right here. Because when you go down 2, you end up at -2, right? Normally. Okay, so going down 2 and over 1 would take you right here. Now, if I draw that line right there, do not draw it too dark like we talked about. It is going to look like this right here. Okay. Don't draw it, again, don't draw it too dark. Okay. But what part do I want to keep? Just the part that is to the left of -3. So what I'm going to do is I'm going to erase off the rest of it here. Okay. And if you already know, if you already know where the graph exactly is going, you can just draw that part of it. It's just that it's kind of hard to do that when the graph starts way over here. It's just easier, I think, to graph the whole thing and then erase off the part that that you don't need. Okay. Is there an open or closed circle right there? Well, since the inequality next to the -3 here for the first formula does not have a alligator foot underneath it, that is going to be a, as you guys now know, that is going to be a open circle. Okay. Now you might be wondering, okay, is that open circle in the correct place? The way to find that out is to figure out where the change takes place, okay, or what happens at that change. Okay, remember we said that we got to plug in -3, and also we're going to plug in 2 as well, because it changes at -3 and at 2. So if I plug in -3 into the first formula here, I'm going to get -2 times 3, or pardon me, times -3, and that is equal to 6. Is that the y value right here, you guys? It is, okay? That open circle is at y equal to 6, so we graphed it correctly. If we didn't, then we can slightly adjust it, okay? But we did it correctly there. By the way, you don't need to plug in the -3 into all three of these, just in the two formulas where it changed, which is, as you can see here, the first and the second. So I'm going to plug the -3 also into the second one here. I'm going to need that on the next part of the problem here, so I might as well do it. And I end up getting -10. So when I graph the next part here, it's going to end at -10 right there. You'll see what I mean here when we graph it. So let's graph the next part here. But doing that 6 right there, it just assured me that that open circle was in the correct place. Okay, like we talked about before. So let's see here. This one right here, it starts out at the -1, which is halfway between 0 and -2 there for the B. But then because we're going up 3 and over 1, going from -1 up to 2, isn't that a distance of 3 right there? From -1 to 2. If we're in Chicago and we increased from -1 degrees to 2 degrees, isn't that a 3-degree increase? Okay, so I know it's just kind of weird looking at it on the graph here, but that it does go up 3 degrees when you do that. And so it goes up 3 and over 1, and then here is the line right here. Okay. So, like that, and then like that. Okay, but what part do we keep? We keep just the part that is sandwiched between -3 and 2. So I erase off the portion of the graph that is in between -3 and 2. Okay, and we just keep that part right there. Okay. All right, but remember, we can't put arrows there anymore because they end. Arrows mean it goes on forever. So we've got to use our open and closed circles in order to end these graphs right here. The reason why this has an arrow on the end is because it does go forever in one direction, okay, but not the other, okay, because it ends at -3, but then it's to the left of -3. That means it's forever to the left of -3. But here, because it's sandwiched between -3 and 2, that means it's trapped on both sides. It stops on both ends. It stops going this way at 2, and it stops going this way at -3. That's the difference. All right. Usually what's going to happen is the first and the last part of the piecewise function will have an arrow on one end because it'll go forever to the left and forever to the right. But it's that one, if you have one that's in the middle here, when you got 3 of them, that one is going to be sandwiched between where you'll have open or closed circles on both ends of it. Okay. So what are they? Well, since both of these have alligator feet right here, that means that both ends have closed circles on it. But are those closed circles in the correct place? Again, the 2 and the 2, the second and the third formula, those are the two formulas that change at 2. So that means that we need to plug in the 2 into the second and third formula to make sure that those two closed circles that I just drew are in the correct location. All right, let's find out. 3 times 2 minus 1. Again, I'm plugging it into the second and third one. So I get this first one right here is 6 minus 1, which is 5. And the other one is -8, isn't it? Let's see if we did it right. Okay, it looks like I'm a little bit off on this one right here. Okay, negative 8 is actually right here, so I need to slightly adjust it. I just need to kind of tweak my graph here, my line a little bit here. Okay. So the negative 8 is actually right there. Okay. Let's see. Oh, you know what? Wait, hold on just a second. Let me make sure I did that right. Oh. I apologize, you guys. I was looking at the wrong number there. Let me back up. I apologize. That's I had it right the entire time right there. In fact, actually, I needed to go down one. So let's put that back on there. But before I do that, this number right here is for the negative 10. Okay. There's negative 10 right there. Notice it says it changes at negative 3. That means that the two circles, open or closed, that are at negative 3, okay, are going to be for these two numbers that are for negative 3. Here's the negative 3 numbers right here, okay? And then here are the x equal to 2 numbers right here. So these two numbers are where the two circles are that are sitting right above and below the negative 3. So the 6 goes with this one because that comes from the first formula. Because this graph right here is with the second formula, that's why the negative 10, which you can see I plugged it into the second formula to get that, the negative 10 would then be on the on one end of that graph there. That's the second formula. Okay, so that's what I need to do right there. I apologize for the confusion right there. And so that's going to be negative 10, and you can see that that lines up. And then this one actually is going to be 5. Now, it looks like it's 6. You know what? That's pretty close to 5. I would accept that answer if you gave that, okay? It looks like it'd either be 5 or 6. Let's just kind of make it look more like it's 5 right there. But what's important is that it is on the 5 right there. And if it, I know... Okay, so what's important is that the x that the closed circles there are on the correct spots there approximately. Okay, as long as it looks like it is, that's what's important. Okay, so we got those two closed circles done right there. All right, so the 6 and the negative 10 are for the numbers that are above and below the negative 3, where x is equal to negative 3, and then the 5 and the negative 8, they are for the numbers that are at x equal to 2. So I did the 5 because that came from the second formula, and this piece right here is the second piece. So that's why it goes to, that's why the 5 is here. So you might be wondering, well, what do we do with the negative 8? Well, the negative 8 is going to be, let's bring that down here, and it's going to be an open circle because the third graph here, which this negative 8, I plugged it into the third graph, or the third formula rather, to get that, okay? So I know that the third part of the graph that comes from negative 4x, I know that that open circle is going to be a part of that because that negative 8 comes from the third formula. Okay, and since it changes at x equal to 2, this is going to be the beginning of the graph right here. But what's the rest of it? Okay, well, we know that when we graph negative 4x, it is, again, and we're going to erase off a lot of this eventually, but it means that it starts out at b equal to 0. We go down 4, which is just 2 marks right here because we're counting down by 2s. And then you go over 1. And you can see what's going on here. You see how this goes down like this, and then it hits that open circle right there. Okay? So what we do then is we just erase off the part that we don't need. It says that we're only supposed to keep the part that is to the right of the 2. That would be this part right here, wouldn't it? Okay? And so we keep that, and then we erase off the rest of it. Go ahead and do that here. Okay. And so and then you just keep the part that you need. Okay. So that is why the piecewise function looks like that. 3 different parts, okay? Figure out what the 3 graphs will look like, but only keep the parts that you need, Okay, sorry, I need to zoom in there, don't I? Okay. I apologize. Okay, I didn't zoom in there right away. So again, we just keep the part that is to the right of the 2, graphing the negative 4x, all right? And then we put the open circle where the negative 8 is there, okay? Because that was from the third formula right there, okay? So that's the beginning of the third piece of the graph, all right? And so I put that down there, but then I didn't keep any of the other part of the line that you would normally draw for negative 4x, all right? So let's go ahead and wrap up this problem right here. Okay, we've got all of that. All the different pieces are there. Let's summarize that. Again, don't forget to figure out just where it changes here. If it changes just between these two, then you only need to plug negative 3 into the first two. And since 2, it changes the second one to the third one for 2. You only need to plug 2 into the second and the third one. Okay, and so that's it for that. In this last part right here at the bottom, we're going to do the opposite thing. Now this time we're actually going to have the graph first, and then you have to come up with the function formula with the different parts, okay? And when I say the different parts, I mean the part where it tells you what f of x is equal to, and then over here it tells you what x values that counts for, and it'll have, inequalities usually and stuff like that. We'll talk about that here in 4, 5, and 6. Here we go. In number 4, notice it's got 2 parts to it. The graph does 2 different pieces. Again, that's why we call it piecewise. Notice the first piece, though, goes to the left of, what is this number right here? This is x equal to negative 1 right here, right? Okay. It goes to the left of negative 1, okay? But it also goes right up to, and it actually has an open circle at negative 1. Let's talk about that. So remember, when you go to the left of a number, in this case to the left of negative 1, that means that you are what? You are x less than negative 1. Okay, but because it has a closed circle right there, remember a closed circle is associated with what? It's associated with when you have alligator feet, okay, as we saw in previous problems. Okay, if you've got a closed circle, that's got to give you alligator feet. So when we're actually figuring out what the formula is, if you've got a closed circle, we'll use the alligator feet right there. Okay, so this first one here, and leave some space here because I haven't figured out what the formula is yet. I just want to know what the x's are. I want to know what this second part is. Okay, I want to know what that is right now first. Okay. So, in fact, let me give myself a little bit more room right there. But it is going to be that same thing. X is less than or equal to negative 1. Okay. If x is less than or equal to negative 1. If. Okay. All right. So now, what is the deal with this other part here? Okay. Sometimes there's a huge break like that where the negative 1 doesn't start back. In other words, the next part of the graph doesn't start back up in the same spot where this one left off at negative 1. Sometimes it's a huge break. That's okay. That's sometimes happens. Okay. Let's just take a look at it, though. Notice that it goes to the right of this number right here, which is x equal to 2. Okay, x equal to 2 right here. And so because it goes to the right of 2, we're going to say x is greater than 2. Right? To the right of 2 means greater than 2, just like to the left of negative 1 means less than negative 1. Okay, but do we put the alligator feet here this time underneath this alligator that's next to the 2? No, we do not. No, we do not, because this has an open circle. Again, open circle means no alligator feet right there. So, all right. Okay. Now, what are the formulas, though? Okay, well, as you guys know, horizontal lines are, as we saw in the last section, 2.5, horizontal lines are the ones where you just have y equal to something. Or in other words, f of x is equal to something, okay? And so since f of x is what these things are going to be equal to here, when you have a horizontal line, you're just going to have one of these just constant numbers. You're not going to have any variable in there, okay? Both of these are going to just be constant numbers here. No x inside of those. Okay, just like we saw up here. Remember up here, when it was just a constant number, it was a horizontal line, right? Okay, same thing here. Since both of these pieces are horizontal, we're just going to have constant numbers here. All you got to do in order to figure out what those constant numbers are is figure out what the y value is there. Okay, so in other words, if the line goes parallel to y equal to 1 right here, in other words, if you were to graph this entire line, it would go through y equal to 1. Since it goes through y equal to 1, if you look at the whole thing, okay, and this is just a piece of it, but if it did go all the way through, it would go through y equal to 1. That means that this first piece right here is just equal to 1. And since this is also a horizontal line, it's also going to be just a constant number, no x. And because if you graph the whole thing all the way through, it would go through y equal to -1. That means that this point right here, or this number, is going to be -1. And that's all you got to do. That is the entire answer right there. Okay. Obviously, I could have made a little bit more space there, but the important thing is that we got it written down correctly there. Let's move on to the next one here. In number 5, we again have two different pieces. Okay, one of them is horizontal, so that means that the first piece will just be a constant number. This other one here, though, resembles one of our basic graphs in the front. We'll take a look at that one thing at a time here, though. Let's start out by looking at the conditions. Okay, if what? If in other words, I'm going to have two parts here, okay, because it's got two pieces to the graph. The first part is to the left of 0, isn't it? To the left of x equal to 0. Since it's to the left of x equal to 0, we are going to say if x is less than 0. Remember, less than means to the left. So less than 0 when it's to the left of 0. Do I put the alligator feet underneath the alligator mouth right here? Do I put the equal to thing there? No, I do not, because that's a open circle. So just say less than 0, not less than or equal to 0. Now this other part here, and I'll get to the formula in a minute, but what is the if part? Okay. First of all, notice that it goes to the right of 0, to the right of x equal to 0. When we go to the right of 0, that means that we say greater than 0. But are we going to put that little equal to thing, the alligator feet, underneath that? This time we are going to say greater than or equal to 0 because it's a closed circle right there. Closed circle means that we, again, use the alligator feet there. So those are your two different conditions. Which formula goes with each one? Let's start out with the first one there. Since that's horizontal, it's just going to be a constant number. And just like in the last problem, you just got to look at where it goes through the y-axis when it's a horizontal line, and that will tell you the number that it is. You can see here, if you count down, that this is 1, 2, 3. So that would be at -3 right there. -3. Okay. And so, and again, that's what you do with horizontal lines. It's just a constant number. You just got to figure out the y value. This other one, though, resembles this graph right here. Okay, let me come up a little bit so you can see it better. Actually, let me zoom out too. There we go. There we go. Okay, and let me move it up to there we go. All right, now, notice please that this point right here is 1, 1. And this point right here is 4, 2. Just like it says right here, 1, 1. This is the front of your worksheet. 1, 1, and 4, 2. So this must be the correct graph. It is square root of x. So we just say square root of x. Remember, the f of x is already over here, so you don't need to say that again. Just say square root of x because f of x is equal to square root of x. Okay, so now you have the formula for both. And we're done with that. Okay. All right. And then finally, the last one here. This one's unusual, okay, because it's got like a pothole in the road, and it looks like somebody took a pothole out of the road and just dropped it somewhere else, aside from the road. Let's find out how to describe all that mathematically here, okay? First of all, when you have a graph that is completely continuous on both sides of an open circle, see how it's completely continuous to the left of the open circle and completely continuous to the right? What we do in that case is this. We just simply say if x is not equal to, you put a slash through the equal sign, x is not equal to, and then what is the x value where the pothole is right here? The open circle. It's at x equal to 2, right? So we say if x is not equal to 2. What that means is whenever you say x is not equal to 2 in this type of situation, it means that you are saying that every single other number besides x equal to 2 is going to apply to this first formula here. Okay, so if I said, for example, x is not equal to 4, then that means that the first formula would apply to every single number except for 4. It's just the way that we write it here. Okay, and so if you have that type of situation where the graph is continuous on both sides of 2, that's what you do. And then if there's a separate point where that open circle is located, where the actual point jumps to somewhere else, in this case it jumped up a couple spots, then we need to have a second thing right here, a second condition where x is equal to 2, and then that part right there will describe where the point jumped to. Okay, so let's talk about that. What is the formula for the first one here? Since it's a line, okay, we can then come up with the line for that. And we did that actually in the last section when I showed you, remember when I showed you a line and you had to come up with the m and the b and then eventually the equation from that just by looking at the line? We're going to do exactly the same thing here. Okay, remember we figured out what the b was by looking at where it crosses through the y-axis, and then we figured out what the slope was by going from one point to the other. Okay, we're going to do that exact same thing here. Okay, so notice here that this is b, right? B is equal to -2. You can see that there. You can also, oh my bad, I'm sorry, that's -3. You've got to be careful there. -3. All right. And so we then jump up 2 and go over 1. We rise 2 and go over 1 to move from a point on the left, just like we did over here. To go from a point on the left to a point on the right, we have to rise and go to the right. So that made it a positive slope. Same exact thing here. We got to rise 2 and run 1. Let me write that down. Rise 2 and run 1. Since we'd rise and run to the right, that makes it positive. What kind of equation would we have if we do it the same way we did in the last section? What kind of equation will we have when we have m and b equal to those numbers? We would have y equal to 2x minus 3. Okay, just plugging in the m and the b where they normally would go. And so that means that f of x is equal to, you don't have to write down this extra step here, and we already know that y and f of x are the same, but that means that f of x is equal to 2x minus 3. All right, and so we take the 2x minus 3 and we put it right there. Okay, let me zoom back in here now that we're ready to finish off the problem here. So that's the line, okay, and that the line is true anytime x is not equal to 2, and so that's why we put in the first spot there. Where is, now remember again, when we actually figure out this formula here, those are y values right there, okay? That's the reason why this over here was -3, is because the equation was y equal to -3. So it makes sense then that we figure out what the y value is right here and then put that here, okay? since y is equal to 3 right there, that's what we're going to put there. Now, you might be thinking at this point, wait a second, I thought that when we put a constant number right there, it's supposed to be a horizontal line. Yeah, normally it is, but since it's just for one single number equal to 2, it is not. It doesn't have an inequality. Okay, it doesn't have an alligator mouth. It just has an equal sign, which means it is just for one single number when it is an equal sign instead of an inequality. That's why this is not a horizontal line right here, even though it looks like one when we just write down a constant number like that. Okay, so don't be alarmed by that. It doesn't mean that it has to be a horizontal line when it's an equal sign like that. It's just supposed to be a single number and therefore a single point, okay, when you have the equal sign like that. And so there's number 6. Okay, so that is how you figure out the piecewise defined function formula, okay, from looking at the graph, all right. Let's go back to that first problem on the front side of the worksheet now. Okay, we've kind of talked about it already, so we should be able to handle it okay. But let's take a look at that carefully here to wrap things up here in this section. When they ask us actually for a function value, and we talked about this in the last section, where do you plug in a function value? Okay, please remember, there are 3 different formulas here. So how do you know which one to plug it into? Do you plug it into all 3 of them? No, you don't. Notice that -5 is where it is. And again, we're not graphing here, so you don't need to plug it into a couple of them or any of that stuff like we did before. -5 is where it is. Notice here that when x is less than -3, that means it's what? It's to the left of -3. Okay, again, you don't have to graph this. But which one of these 3 things right here, agrees with -5? Okay, in fact, let me bring that down here. Let's bring down f of -5. Let's bring down f of -1. We can kind of just look at it carefully here down here. And then 3, f of 3. Where is -5 located? Remember, we're looking at x equal to -5 right here. That's what we're plugging in. That number inside that bracket is an x number. Okay. Where is -5? Well, if I plug it into here, isn't that going to be true? -5 is less than -3, isn't it? But -5 is not between -3 and 2, is it? Remember, when x is in the middle like this, then that just applies to numbers for x that are in between -3 and 2. So -5 is true here in the first one, but not true in the second one, and it's certainly not true down here either, because -5 is not greater than 2. So when you figure out which one to plug it into, just plug the x number into each one of these 3 things, and only one of them is going to be true. Only one of them is going to be true. If none of them are true, that's also a possibility. Then that means that you can't figure out what that number is. I'm not going to give you one of those normally. But normally, one of them will be true. Figure out which one it is. Since the first one is the one that's true, then that's the one you plug it into. And so all you got to do is just plug it into -2x. And my final answer is 10. And that's all you had to do there. Okay, so it's a pretty short problem. It's just a matter of knowing where to plug it in. Okay. Now, where does -1 go? -1, again, let's test it out. Is -1 less than -3? No, that's false. Is -1 in between -3 and 2? Yeah, it is. Okay. Just like if it was -1 degrees in Chicago, that means that it's between -3 degrees and +2 degrees, isn't it? Okay. So, same thing here. So, that's the true one, isn't it? Okay, you don't need to test the last one now because you already know that the middle one is the one that's true. Okay, you're not going to have more than one that's true in this particular case. So plug it into the middle formula because it's the middle one that it applies to, since that was the one that was true. What do we get here? We get -3 minus 1. I'm just doing order of operations here, just like we did before when we were plugging numbers into f of x, and I get -4. Okay. And then the last one, same idea here. Which one is true for 3? X equal to 3, you guys. Remember, this is x equal to 3 here. The only one that is true is the last one. And so that means we plug in 3 into the last one. Okay, you gotta, again, the key thing in all of this is to plug it into the correct one. You don't plug it into all of them. You plug it into the one that is true, okay, for x. And that's going to be negative 12 when I plug it into that last one, isn't it? Okay, so there's your three final answers right there, 10, negative 4, and negative 12. Okay, so that's our discussion on piecewise defined functions, you guys. And so, again, be careful to remember that each part of the piecewise defined function is it's only for a certain part of the graph, depending on how x is defined. Okay. So again, as always, let me know. Contact me if you have any questions. Take care.